Okay, welcome to the deep dive. This is where we take your stack of sources, articles, research, your notes, and distill them into the absolute most important, most insightful nuggets of knowledge, giving you that shortcut to being well-informed. Today, we're tackling a skill that's foundational, powerful, and honestly, a bit legendary in the tech world, learning C++ math.
It certainly has a reputation, doesn't it? Often seen as one of the more challenging languages to pick up, perhaps a bit daunting at first glance.
Definitely daunting.
But as the comprehensive guide you've shared makes incredibly clear, it's also one of the most rewarding, opening doors to fields where performance and control are absolutely paramount.
Absolutely. And this deep dive is specifically tailored for you, our listener, who's looking to step into the world of C++ when maybe you're wondering where to start, how to navigate its different complexities, or just trying to get a clear mental map of the learning journey ahead.
Exactly. The material provides a fantastic roadmap, really. It covers everything from the absolute basics of syntax and structure through essential constructs like pointers and memory,
Oh, yeah.
diving into object-oriented programming, exploring the power of the standard library, and importantly, offering practical strategies on how to learn it effectively.
So our mission today is to cut through that volume of information. We're going to extract the most critical insights, shine a light on what learning C++ truly involves, break down those intimidating concepts with enough detail to make sense, and hopefully give you a clearer path to navigate it efficiently.
Right, helping you get to those aha moments and build confidence quicker.
Let's unpack this journey.
Let's do it.
Right. So let's start at the very beginning. What is C++ at its core, and why does it occupy such a significant and often, well, unique space in the programming ecosystem?
Good place to begin. The source material traces C++'s origins back to Bjarne Stroustrup at Bell Labs in 1979. It didn't start as C++ right away. It was initially an extension of the C language, specifically designed to add object-oriented features.
Right, building on C.
Exactly. Stroustrup originally called it C with classes.
C with classes, that name alone tells you so much about its foundation and initial purpose, doesn't it?
Precisely. It was a pragmatic approach, really, to bring the benefits of OOP to a language already known for its close-to-hardware performance. The name C++ came later, officially around 1982-1983,
Okay.
and the first commercial release followed in 1985. So it's a language with deep roots, fundamentally built upon C, inheriting its efficiency and low-level capabilities.
And it certainly hasn't stayed static since 1985. The guide highlights its continuous evolution.
Not at all. Unlike some languages that might have fewer fundamental shifts, C++ has been rigorously standardized by the ISO, that's the International Organization for Standardization, and this has led to major revisions.
It's like the different versions, C++ 98.
Yeah, we had C++ 98, then a minor update with C++ 03, and then a truly transformative release in 2011 with C++ 11.
C++ 11, that's often cited as the birth of modern C++A, isn't it? What made it such a game changer?
It really was a leap. C++ 11 introduced features that fundamentally changed how you write safe, efficient, and expressive C++ code. Think things like lambda expressions for concise functions.
Tremendous. Yeah.
Smart pointers for automated memory management, which is a huge GE deal. We'll definitely talk more about those.
Oh, excellent.
And the auto keyword for type deduction, which cuts down on some of the verbosity. It made the language feel significantly more modern and safer right out of the box.
And it didn't stop there.
Nope. The evolution has continued with C++ 14, C++ 17, C++ 20, and now C++ 23, each adding more refinements and powerful capabilities. Learning C++ today absolutely means learning modern C++. You really want to focus on C++ 11 and later.
So it's a living, breathing language that keeps improving. The source also describes it as a multi-paradigm language. What does that imply for a learner?
It means C++ doesn't lock you into one single style. You can write procedural code, much like you would in C. You can leverage the full power of object-oriented programming with classes and inheritance.
The OOP stuff?
Yeah, or you can use generic programming, which is kind of the magic behind the standard template library, the STL, allowing you to write code that works with any data type. This flexibility is a key strength.
And the description as a middle-level language, what's that about?
That's a crucial characteristic that defines C++'s unique position. It successfully bridges the gap between high-level languages, the ones offering strong abstractions like Python or Java.
Easier to start with sometimes.
Right. And low-level languages that provide close control over hardware, like C or assembly. C++ gives you powerful high-level features like objects and templates, while simultaneously giving you direct, fine-grained control over memory and system resources, which it gets from C.
So high-level convenience plus low-level power?
Exactly. This duality is what makes it so powerful for specific domains, where you need both abstraction and control.
Okay, that gives us the what and a sense of its technical makeup. Now, the big question. Why learn C++ today? With so many other languages out there, why invest the time in one often seen as, well, difficult? The source material lists key features that answer this directly.
Right. And the first one, often the headline feature, is its fast execution speed. Because C++ code is typically compiled directly into machine code tailored for the specific hardware.
No intermediate layer, usually.
Exactly. The resulting applications are incredibly high performance with minimal runtime overhead. The source rightly points out it's one of the fastest high-level languages available, period.
Speed matters for a lot of applications. Gaming, finance.
Absolutely. And that speed is often paired with its ability for low-level memory access. This means you, as the C++ programmer, can control exactly where and how data is stored in memory, manage system resources like files or network connections directly.
Really get your hands dirty with memory.
Yeah, which is critical for performance-sensitive applications, or when you need to interface closely with hardware, like in embedded systems.
That low-level control sounds powerful, but also maybe potentially dangerous, which I'm guessing we'll get into later.
Oh, indeed. We definitely will. But balanced by that is the object-oriented programming, OOP support. C++ fully supports encapsulation, inheritance, and polymorphism. These OOP principles allow you to structure large, complex programs in a modular, organized, and reusable way.
Makes coding big projects more manageable.
Definitely. So you get the benefit of OOP design principles combined with that low-level power. It's a potent mix.
What else?
Another advantage is its machine independence or portability. Now, you need a compiler for your specific target platform, obviously.
Right, you have to compile it for Windows or Linux or Mac.
Yes. But well-written C++ code can be compiled and run on a wide variety of operating systems and hardware architectures without major changes.
And you don't have to build everything from scratch, right? The standard library.
Far from it. The rich standard library, STL, is a massive advantage. It provides a huge collection of pre-built components. Think everything from containers like dynamic arrays, which are std.vector,
We'll definitely talk about vector.
and maps, std.map, to powerful algorithms for sorting, searching, manipulating data, you name it. Using the STL saves immense development time and provides highly optimized, well-tested code.
It's like having a toolbox filled with extremely efficient, ready-made tools.
Precisely. And for developers coming from related languages, the source notes its syntax similarity to C, Java, and C#. While there are significant differences, let's be clear, the basic syntax for loops, ifs, variable declaration. It could feel somewhat familiar.
Might ease the transition a bit for some people.
It potentially could, yeah.
So connecting those features to the real world, or as C++ actually used, the source material provides a compelling list of diverse applications.
It does, and this really shows the impact of C++ capabilities. Because of its performance and control, it's fundamental in building operating systems. You'll find C++ in large parts of Windows, macOS, and Linux kernels and core components.
Wow, so the very foundation of our computers often relies on C++.
Yes.
Yeah.
It's also the dominant language in game engines and development. Think high-performance engines like Unreal Engine.
A classic example.
Right, built with C++ wool down. Speed and direct hardware control are just essential for complex graphics, physics simulations, and the kind of real-time responsiveness you need in gaming.
That makes perfect sense. Where else is speed and control critical?
Web browsers. Core components of major browsers like Chrome and Firefox, particularly things like the rendering engines and JavaScript engines, heavily use C++ for performance.
Okay.
Financial systems, especially in high-frequency trading, HFT platforms, and banking infrastructure, absolutely rely on C++ for speed, reliability, and precision, where milliseconds, even microseconds, can mean huge amounts of money.
Yeah, you can't afford delays there. Mission-critical stuff.
Exactly. It's also crucial for embedded systems. The software running on microcontrollers and devices that interact directly with hardware. Think automotive systems, IoT devices, medical equipment.
Things where software meets the physical world.
Precisely. And interestingly, many compilers and IDEs themselves, the very tools programmers use to write code, are actually written in C++F.
building the tools with the tool itself. That's quite a statement.
It's a testament to its power and ability to handle complex system-level tasks. It's also used extensively in graphics and multimedia applications, rendering, video processing, things like that.
Yeah.
And as you often see on platforms like LeetCode or HackerRank, it's a primary language for competitive programming because of that raw efficiency and control it offers.
So learning C++ isn't just about, learning another language. It gives you a deep understanding of computing foundations and opens doors into these really high-performance, demanding fields.
It provides a level of insight into how software interacts with the machine that is truly invaluable, frankly, regardless of what language you ultimately specialize in. You understand things differently.
Okay, before we even type #include IOStream, we need a place to actually write and compile our code. The source covers setting up the environment.
Right, the practical first step. You'll need the essential tools.
Right.
A C++ compiler. That's what translates your human-readable code into machine code.
The translator.
Yep. An integrated development environment, IDE, or maybe just a good text editor paired with command line tools. And potentially, for bigger projects, build tools like Make or CMake to manage how everything gets compiled and linked together.
Any specific compiler or IDE suggestions from the source for someone just starting out?
Common compilers mentioned are GCC, the GNU Compiler Collection, Clang, often popular on Mac Linux, and MSVC, Microsoft Visual C++ on Windows. For IDEs, popular choices are VS Code, Visual Studio Code,
Very popular choice.
.code.blocks, Eclipse, or the full Visual Studio IDE from Microsoft. The source often suggests VS Code for beginners because it's flexible, relatively lightweight, and has great C++ support through extensions.
It sounds like choosing and setting up can be an early hurdle, though. Just getting everything installed and talking to each other.
It absolutely can be. The source acknowledges this. It's not always just click and install. You might need to configure paths, tell your IDE where the compiler is.
Yeah, fiddly stuff.
It can be. This is why finding and following a clear step-by-step installation guide specifically for your operating system and your chosen tools is highly recommended. Avoids a lot of early frustration. Good resources like learncpp.com usually have excellent setup guides.
Practical advice: find a good guide and stick to it initially. Don't try to wing it.
Exactly. And crucially, the source emphasizes the importance of configuring your compiler correctly right from the start. This involves selecting the C++ language standard you want to use.
Not just using the default.
No, you absolutely should choose a modern one, like C++17 or C++20, maybe even C++23 if your compiler supports it well. Don't start with an old standard like C++98 or C++03.
Why is picking a modern standard so important from day one?
Because modern C++ standards contain features, libraries, and best practices that make code safer, more efficient, and frankly, just easier and more pleasant to write. Starting with an old standard is like learning to drive using a map from the 90s. The roads have changed.
Good analogy.
Also vital is setting warning and error levels high in your compiler settings. You want the compiler to complain as much as possible.
High warnings. Doesn't that just give you more errors to fix? Seems counterintuitive.
It does, but that's the point. It catches potential issues before they become hard to debug runtime bugs or subtle logical errors. High warning levels enforce good coding practices, things like initializing variables properly, being explicit about type conversions.
So it acts like a strict coach.
Exactly. It prevents bad habits from forming. This early vigilance saves immense time and headache down the road. It's really a fundamental modern C++ practice. Get the compiler to help you as much as it can.
So get the tools set up right, pick a modern standard C++17 or newer, and turn up those warnings.
Got it.
Once the environment is ready, the traditional first program is Hello World. Its main goal isn't really anything complex. It's simply to confirm that your compiler is working, your IDE can build and run the code, and everything is hooked up correctly.
Just a sanity check for this setup. And the source provides that basic structure.
It does. It shows you need a #include IOStream to bring in the input-output stream library. You need the int main function. That's where your program execution begins.
Always main.
Always main. Then std.count hello world to print the message using the standard output stream count and the insertion operator. And finally return 01 to tell the operating system the program finished successfully.
The minimal working program.
Yeah. It's the first hurdle, cleared your tool's work. All right, environment checked. Let's move into the fundamental building blocks of the language itself. This is where the actual coding begins with syntax and basic elements.
Right. Every C++ program has a structure. Often, it starts with preprocessor directives. These are lines beginning with hashtag, like that hashtag include we just saw.
The hash symbol.
Yeah. These are instructions for a program called the preprocessor, which runs before the main compiler. It often does things like including the contents of other files. Hashtag include IOStream. Basically pastes the definitions needed for input and output into your code before compilation.
So hashtag means do this first.
Pretty much. And then, as we said, program execution always kicks off in the main function. Every C++ executable must have exactly one main function.
Within main or any other function, you have statements.
These are the basic units of execution, the individual instructions for the program. In C++X, statements typically end with a semicolon may.
A semicolon, gotta remember that.
Absolutely. The semicolon is the terminator for the compiler. It marks the end of a single instruction. This gives you flexibility. You can put multiple short statements on one line or spread one long statement over multiple lines for readability, but the semicolon ends the instruction.
And to make that code readable for humans, not just compilers, we have comments.
Indispensable. Comments are notes for developers, completely ignored by the compiler. You have single-line comments, starting with which go to the end of the line,
Like quick notes.
and multi-line comments enclosed in play, which can span several lines. Good commenting habits are essential for writing understandable and maintainable code, both for others and, trust me, for your future self when you look back at your own code.
Definitely helps future you. Okay, now to actually work with data, we need variables, data types, and constants.
Right. Variables are essentially named locations in memory where you can store data that might change while the program runs. Before using a variable, you absolutely must declare it. This means specifying its data type and giving it a name, like int number of students.
And data types dictate what kind of data a variable can hold and how much space it takes.
Precisely. They define the kind of values, like whole numbers, decimal numbers, characters, the range of those values, the operations you can perform on them, and how much memory the variable will occupy. C++ is a strongly typed language.
Meaning the type is fixed.
Yes, a variable's type is fixed when you declare it at compile time, and the compiler strictly enforces type rules. This catches a lot of potential errors early on before the program even runs.
What are the fundamental built-in types? The primitives.
The source lists the basics. Int for integer or whole numbers. Float and double for floating point numbers. Numbers with decimal points, float is single precision, double is double precision, usually bigger and more precise.
Double is often the default for decimals.
Often, yes. Then you have char for storing individual characters like a or doll. Bool for Boolean values, which can only be true or false. And void, which means no type, often used to indicate a function doesn't return a value, or for generic pointers, which we'll get to. The guide usually mentions their typical sizes in bytes, though that can vary slightly between systems.
It feels like there are a lot of options just for numbers. Int, short, long. Why so many variations?
That's part of C++ as a design philosophy, coming from C giving the programmer control. Having different integer sizes, short, int, long, and at floating point precisions, lets you choose the best fit for memory usage and performance. If you're working on an embedded system with tight memory constraints, using a short instead of an int might matter.
So it allows optimization.
Exactly. Though for a beginner, int, double, char, and bool are the most common starting points. You don't need to master all the variations immediately. The source also mentions data type modifiers like short, long, signed, unsigned, which can alter the range or interpretation of these basic types.
Okay, and constants, things that don't change.
Right. Constants are values that, once set, cannot be changed during the program's execution. You define them using the const keyword, for example, const double pi equals 3.14159. Using constants is great for readability. Pi is clearer than 3.14159 scattered everywhere, and it prevents you or someone else from accidentally modifying a value that shouldn't change.
Good practice for maintainability.
Definitely. And literals are just the raw values themselves written directly in the code.
Exactly. Literals are the actual fixed values you type in, like that number 42, the floating point value 3.14f. The f often denotes float, the character a, or the string hello.
The source also makes a key distinction between initialization and assignment. Sounds subtle, but important.
A very important one. Initialization is giving a variable its first value when you declare it, like in score equals 100. Assignment is changing the value of a variable that already exists, that has already been declared and possibly initialized, like score equals 150 later on.
And the danger is using them before they have a value.
Precisely. The guide correctly warns that using variables before you've given them a value, either through initialization or assignment, leads to undefined behavior. The variable will contain some garbage value left over in memory, and your program's outcome becomes unpredictable. It might seem to work sometimes, crash other times.
Nasty bugs.
The worst kind. So, rule number 1, always initialize your variables. Give them a sensible starting value right when you declare them.
Undefined behavior. That's a phrase we're going to hear again, I suspect.
Absolutely. It's one of the trickiest aspects of C++ if you're not careful.
Moving on, we have operators. These are the symbols that let us perform operations on our data, on our variables and literals.
Right. C++ has a rich set of operators, many inherited directly from C. You have the arithmetic operators for mathematical calculations, plus, minus, times, divide, and the percent for modulus, which gives you the remainder of a division.
Standard math stuff we learned in school.
Pretty much. Then assignment operators. The basic one is equals. But you also have shorthand operators like plus equals would combine an operation with assignment. So x plus a equals 5 is the same as x plus 5.
Saves a bit of typing.
Exactly. Then comparison or relational operators. These are used to compare two values, and they always result in a Boolean true or false. You have for equality is equal to.
Double equals.
Yes, double equals for comparison. For inequality is not equal to. And then equals for less than, greater than, less than or equal to, greater than or equal to.
And the source flags is a super common beginner error right here. Mixing up the single equals for assignment and the double equals for comparison.
Oh, yeah, that's a classic. Confusing assignment with equality comparison is probably one of the most frequent syntax and logic errors beginners make. The scary part is, in certain contexts, like inside an if statement, using where you meant it meant might actually compile without an error. But it will do something completely different. It will assign the value, and then the condition might evaluate based on that assigned value, leading to subtly wrong program behavior that's hard to track down.
I could see how that would happen easily. Always double-check your equal signs and comparisons.
Triple check them. What other types of operators are there?
You have logical operators. These are used to combine or modify Boolean expressions. And it's logical AND, true if both sides are true, is logical OR, true if at least one side is true, and a logical NOT reverses true to false and false to true.
Used a lot in if conditions.
Very common. Then increment and decrement operators, plus to add one, and to subtract one from a variable. A small complexity here is the difference between the prefix form, plus x, and the postfix form, x plus.
Oh, right. Pre-increment versus post-increment.
Yeah. They both increment the variable, but when they return, the value in an expression differs. Prefix increments first, then returns the new value. Postfix returns the original value, then increments. Can lead to subtle differences if used inside complex expressions.
Yeah. Another potential gotcha.
A minor one, usually. And for lower level stuff.
There are bitwise operators. Andy, wait. These operate directly on the individual bits of integer data. Useful for certain kinds of low-level programming, hardware interaction, or specific optimization tricks, but probably not something a beginner needs to dive deep into immediately.
Okay, good to know they exist. Now, if you have a complex expression with multiple operators, like A plus BC, how does C++ know what to do first?
That's where operator precedence and associativity come in. Precedence rules define the order, just like PEMDAS or BODMAS in math. Multiplication usually happens before addition, plus. Associativity defines the order when operators have the same precedence. For example, AB plus C is usually evaluated left to right.
So misunderstanding these could lead to bugs.
Definitely, especially if you mix arithmetic, logical, and comparison operators. The source emphasizes, again, the Oakle-Vers confusion, but also just generally not knowing the precedence can lead to calculations happening in an order you didn't expect.
What's the solution?
When in doubt, use parentheses. Parentheses override the default precedence and associativity rules and make your intention crystal clear, both to the compiler and to anyone reading your code. Using parentheses, even when not strictly necessary, can often improve readability.
Good tip. Parentheses for clarity. Don't rely on remembering obscure precedence rules.
Always a safe bet.
Okay, so we can store data, we can operate on it. How do we make the program smart enough to make decisions or repeat actions based on conditions? That sounds like control flow?
Exactly. This is fundamental to making programs do anything interesting. Control flow statements alter the normal sequential execution of instructions, one after another, allowing programs to branch based on conditions or loop to perform repetitive tasks.
Starting with conditional statements for decision-making, the if statement.
Yes, the most basic is the simple if statement, is condition. Code to run if condition is true. The code inside the braces only executes if the condition evaluates to true.
And if you have an alternative,
Then you use if else. If condition, code if true or false. One block or the other will execute.
And for multiple conditions.
You can chain them using the if-else ladder. If condition 1, condition 2, if condition 3, if none of the above were true. It checks each condition in order and executes the block for the first one that's true.
Okay, that covers branching based on conditions. What about the switch statement?
The switch statement is useful when you want to select one of several code blocks to execute based on the value of a single expression, usually an integer or a character type.
How does it work?
You have switch expression. Inside the braces, you use case labels followed by a constant value and a colon, like case 1. If the expression evaluates to 1, the code following case 1 executes. You can have multiple case labels. There's also an optional default label that catches any value not matched by a specific case.
Seems straightforward. But the source highlights a critical point here. The fall-through behavior. What's that?
Ah, yes, fall through. This is a classic C and C++ feature that trips up many beginners. In a switch statement, if you don't explicitly end a case block with a break statement, execution will fall through into the next case block below it and start executing that code too.
Wait, it just keeps going. Isn't that usually a bug?
It can be, and often is. If you forget the break, you might execute code you didn't intend to. While intentional fall-through is possible, and sometimes useful, though rare, it's a very common source of errors. The strong recommendation is always end each case block, and the default block, with a break statement unless you have a very specific, well-documented reason not to.
Okay, break is the default rule for switch cases. Got it. That sounds important. Now, for repetition, we have loops.
Right. Loops let you execute a block of code multiple times. The three main types in C++ are for, while, and do while.
Tell me about the for loop first.
The for loop is typically used when you know or can easily calculate how many times you want the loop to run. Its header has 3 parts separated by semicolons for initialization, condition, update, loop, body.
So, initialize a counter, check a condition, run the body, update the counter.
Exactly. The initialization runs once at the start. The condition is checked before each potential iteration. If true, the body runs. The update runs after each iteration. It's very common for iterating a fixed number of times or over elements in something like an array.
Okay. What about the while loop?
The while loop is simpler. While condition,
While.
condition, it just keeps executing the loop body as long as the condition remains true. The condition is checked before each iteration.
So if the condition is false the very first time, the loop body might never run.
Correct. The while loop might execute 0 or more times. It's useful when you don't know in advance how many iterations are needed, but you know the condition that should stop it.
And the do while loop.
The do while loop is similar to while, but the condition is checked after the loop body executes.
No.
Do loop bodies to condition. This means the loop body is guaranteed to execute at least once, even if the condition is initially false.
Ah, check after versus check before. That's the key difference.
Exactly. Use do while when you need that guarantee of at least one execution.
And sometimes you need to exit a loop early or skip an iteration.
Yes, that's where jump statements come in handy within loops and switches. We already mentioned break, which immediately exits the innermost loop or switch it's contained within.
Gets you out completely.
Right. Then there's continue. When continue is encountered inside a loop, it skips the rest of the current iteration of the loop body and jumps straight to the next iteration's condition check or update check in a for loop.
Skips the rest of this round, goes to the next.
Precisely. The source also mentions goto, which allows you to jump unconditionally to a labeled statement anywhere in the function. Go to my label. My label.
There's always a but with goto, isn't there? It's generally frowned upon in modern programming.
Yes, very much so. While goto exists, it's strongly discouraged in modern C++ and many other languages. Overuse of goto can lead to tangled, hard-to-follow code, often called spaghetti code. It makes reasoning about the program flow difficult and debugging a nightmare. It's almost always better to use structured control flow constructs like if, switch, loops, and functions. Avoid goto unless you encounter a very specific, rare idiom where it might be justified, and even then, proceed with caution.
Stick to the structured stuff.
Yep.
Got it. So the challenge here for a beginner, it seems, is taking a problem's requirements, the logic of what needs to happen, and correctly mapping that onto the right combination of these control flow structures.
Yeah.
The ifs, switches, fors, whiles.
Exactly. It requires practice to translate human language logic like do this if X happens, otherwise do that, or keep doing this action until Y is true, into the precise syntax and structure of C++ control flow. That translation step is a core programming skill.
Okay, makes sense. Now, to organize code better, avoid repeating ourselves and make programs modular, we use functions.
Functions are absolutely fundamental to writing any non-trivial program. They allow you to encapsulate a specific task into a reusable block of code. This breaks down large, complex programs into smaller, more manageable, and understandable pieces. Think of them as named subroutines.
The source distinguishes between function definition and function declaration. What's the difference?
The function definition is the actual implementation of the function. It includes the function's header, return type, name, parameter list, and the function body, the block of code within curly braces that performs the task. This is where the work happens.
So the code itself.
Right. The function declaration, also known often as a function prototype, is different. It just tells the compiler about the function's signature, its return type, its name, and the types of its parameters, ending with a semicolon. It doesn't include the function body, for example. Int, add int.
Okay, but why do we need a separate declaration if we're going to define the function anyway?
Great question. The compiler reads your C++ code file sequentially, from top to bottom. If you try to call a function before its definition has appeared in the file, the compiler won't know what that function is, what kind of arguments it expects, or what it returns. It throws an error.
So the declaration acts like a forward notice.
Exactly. A function declaration placed near the top of the file, or in a separate header file, which is very common, tells the compiler, hey, there's a function named add that takes 2 integers and returns an integer. Trust me, the definition will show up later. This allows you to call the function before its full definition is encountered, and it's essential for organizing code into multiple files.
Got it. So declaration tells the compiler the function exists and what it looks like. Definition provides the actual code. Makes sense. Inside functions, you have parameters and arguments. What's the terminology there?
Parameters are the variables listed inside the parentheses in the function's definition. They act as placeholders for the values that will be passed into the function when it's called. For example, in int multiply, int x, int y, x and y are the parameters.
Okay, the placeholders in the definition.
Arguments are the actual values or variables containing values that you provide when you call the function. So if you call multiply 5, 3, then 5 and 3 are the arguments. These arguments are used to initialize the corresponding parameters. X gets 5, y gets 3.
Arguments are the real values passed in the call. Clear. And functions can send a result back to the part of the code that called them, using a return value.
Yes, using the return statement followed by the value, or an expression that evaluates to a value you want to send back. The return type specified in the function's signature, like int multiply, determines the type of value the function must return. If a function doesn't need to send any value back, its return type is declared as void.
Void means no return value.
Okay.
And variables declared inside a function. They have a limited existence.
That's right. That relates to their scope. Variables declared within a function, inside its curly braces, are called local variables. They only exist and are accessible within that function's body. They are created when the function is entered, begins execution, and destroyed automatically when the function exits, finishes execution. They are invisible outside the function.
So they're temporary private storage for the function.
Exactly. This helps keep functions self-contained and prevents accidental modification of variables from elsewhere in the program.
The source touches on argument passing methods, specifically mentioning call by value and call by pointer initially.
Right. How arguments are passed to functions is important. Call by value is the default mechanism for simple data types like int, float, char, bool, and also for objects, though copying objects can be expensive. When you pass by value, a copy of the argument's value is made and passed to the function parameter.
A copy, not the original.
Correct. This means any modifications made to the parameter inside the function affect only the local copy. They do not change the original variable that was passed as an argument from the calling code. It's safe because the function can't mess up the caller's original data.
Okay, call by value is safe, passes a copy. What about call by pointer?
Call by pointer is different. Instead of passing the value itself, you pass the memory address of the argument variable using the address of operator when calling, and the parameter type is a pointer like int. Inside the function, the parameter now holds the address of the original variable.
So the function knows where the original lives in memory.
Yes. And by using the dereferencing operator on the pointer parameter, the function can access and modify the original variable's value back in the calling code. This is one way to allow a function to change its arguments.
More powerful, but maybe riskier if you're not careful.
Precisely. The source mentions that call by reference is another important C++ mechanism for achieving similar results, allowing functions to modify arguments, and is often preferred over raw pointers in modern C++ way, but that it will be covered later. So for now, value versus pointer.
Okay, this gives us the structure, operations, control flow, and modularity with functions. Now, how do we actually get data into the program from the user or display results back out? Basic input-output, I/O.
Yeah, programs usually need to interact with the outside world, most commonly through the console, keyboard input, screen output. In C++ way, this is handled using streams, which are defined in the IOStream header file you need to hashtag include.
Streams, like a flow of data.
Exactly. Think of it as a sequence of bytes flowing from a source, like the keyboard, to a destination, like a variable or the screen.
And std.count is for output.
Yes. std.count standard character output is the stream object typically connected to the console screen. You use the insertion operator, which looks like two less than signs, to insert data into the count stream, sending it to the display. You can chain multiple operators together to print different things sequentially.
Like std.count score in.
Perfect example. And you use n there for a new line. Another common way to add a new line and ensure the output appears immediately is using std.endl.
What's the difference between n and std.endl?
Both insert a new line character. The key difference is that std.endl also flushes the output buffer. This forces any buffered output to be written to the console immediately. N just inserts the new line character. The output might stay in a buffer for a short time for efficiency. For simple console output, the difference is often negligible, but endl guarantees immediate visibility.
Okay, endl for new line and flush. For getting input from the keyboard, we use std.syn.
Right. std.syn, standard character input, is the stream object connected to the keyboard. You use the extraction operator, two greater than signs, to extract data from the syn stream and store into variables. It's smart enough to handle different types.
So std.syn's age would read an integer into the age variable.
If age is an int, yes. It automatically tries to interpret the keyboard input as the type of the variable you provide.
And the source mentions a very common, sometimes frustrating point confusion with std.syn and reading strings or text.
Ah, yes. The whitespace issue. This bites everyone at first. When you use std.syn string variable, whether string variable is a C-style char array or a modern std.string, the operator reads characters from the input until it encounters the first whitespace character that could be a space, a tab, or the new line character you press when you hit enter.
So if I type New York and try to read it into one variable,
the variable will only contain new. The space character stops the extraction. Worse, the York and the new line character you typed are left sitting in the input buffer, waiting to mess up your next syn operation.
that could definitely lead to unexpected behavior if you're not expecting it.
It's a classic beginner trap. The source also briefly mentions std.sir and std.clog for error output streams. Sir is unbuffered, meant for immediate error messages, while clog is buffered, perhaps for logging less critical issues. They both usually go to the console too, but can be redirected.
Okay. To handle more complex input properly, like reading an entire line of text, including spaces, the source points to advanced input methods, especially mentioning std.getLine.
Exactly. While there are older C-style functions, the preferred way in modern C++ to read a whole line of text, including spaces, into a std.string object is to use the std.getLine function. The syntax is typically std.getLine, std.syn, your string variable.
So getLine reads everything up to the enter key press.
Yes. It reads characters from the specified input stream, std.syn in this case, until it encounters a new line character. It stores the character's read, excluding the new line itself, into the std.string variable you provide. This is perfect for reading names, sentences, addresses, etc.
That sounds much more useful for user input than just SYNI.
It generally is for text. But the source highlights another subtle but critical issue that often trips up beginners. Mixing std.syn some variable, especially reading numbers, with a subsequent call to std.getLine.
What happens then?
Remember how syn stops at whitespace and leaves the rest, including the new line, in the buffer?
Yep.
Well, when you read a number like synAge, you type the number, say 25, and hit enter. The extracts 25 into age, but the n new line character from hitting enter is left sitting in the input buffer. If your very next input operation is std.getLine, std.name, getLine immediately sees that leftover n in the buffer, since getLine reads until it hits a new line.
It thinks it just read an empty line because the new line was already there.
Exactly. It consumes the new line, stores an empty string in name, and it looks like your program just skipped asking the user for their name. Super confusing behavior.
So how do you fix the leftover new line problem?
The standard fix, as the source implies, is often to call std.synan.ignore right after the syn operation and before the std.getLine call. Syn.ignore can be used to discard characters from the input buffer, and by default, it will discard one character, which is usually that problematic new line. Sometimes you might need syn.ignore, but discard everything up to and including the next new line just to be safe.
Okay, syn.ignore to clean up the buffer after using and before using getLine. That's a really specific, valuable tip.
It's one of those small details that causes a disproportionate amount of beginner frustration until you understand what's happening with the input buffer.
Wow.
Using the right input function for the job and managing the buffer state is key. Streams are type-safe and extensible, which is powerful.
Okay, we've laid the groundwork with syntax, types, control flow, functions, and basic I/O.
Yeah.
Now let's dive into some of the concepts that give C++ plus its legendary power, but also its reputation for being, well, challenging. Pointers and memory addresses.
Pointers. This is where C++ really lets you get close to the hardware, manipulating memory directly. Pointers are fundamental to this, enabling high performance and flexibility. But as the source strongly warns, they're also a primary source of really complex errors if you misuse them.
So what exactly is a pointer, in simple terms?
A pointer is a special kind of variable. Instead of storing actual data, like an integer or a character, it stores a memory address. Think of memory like a huge street of houses, each with a unique address. A normal variable is like the contents inside a house, while a pointer variable stores the address of a house.
Got it. Like a street address. How do you declare one?
You declare a pointer by specifying the data type of the variable it's intended to point to, followed by an asterisk gun, and then the pointer variable name. So int PTR declares a variable named PTR that is designed to hold the address of an int. Double value PTR declares a pointer to a double.
The asterisk signifies it's a pointer type.
Okay.
Yeah, how do you get the actual memory address of a regular variable to store in that pointer?
You use the address of operator, which is the ampersand symbol. So if you have a regular variable like int myValue equals 42, you can get its memory address by writing in myValue. To store that address in our pointer PTR, you'd write int PR equals in myValue. Now PTR holds the address where myValue is stored.
Okay, it gets the address. Now, once the pointer, PTR, holds an address, how do you use it to access or change the value at that address, the value of myValue in this case?
You use the dereferencing operator, which, confusingly perhaps, is also the asterisk tail, but used in a different context, not in a declaration. When you put in front of a pointer variable that holds a valid address, it means go to the address stored in this pointer and give me the value there.
So PTR means the value pointed to by PTR.
Exactly. So int data equals PTR would read the value at the address stored in PTR, which is 42 for my value, and copy it into the data variable. And PTR equals 100 would go to the address stored in PTR and change the value at that location to 100. Since PTR points to my value, this would actually change the value of my value to 100.
Wow, okay. So the pointer lets you indirectly modify the original variable. That seems powerful. The source also mentions null pointers. What are those?
A null pointer is a pointer that is intentionally set to not point to any valid memory location. It's a special value indicating this pointer doesn't point anywhere meaningful right now. It's crucial good practice to initialize pointers to a null value if you don't immediately assign them a valid address.
How do you represent a null pointer?
Since C++11, the standard type-safe way is to use the keyword null PTR. You should prefer null PTR over older C-style macros like NLLL. So you'd write int PTR equals null PTR.
And why are null pointers important, besides initializing?
Because the guide emphasizes a critical danger. Dereferencing a null pointer leads to undefined behavior. If you try to access the value at the location pointed to by a null PTR, e.g. a PTR when PTR is null PTR, your program will almost certainly crash, often with a segmentation fault or access violation. So always check if a pointer is null before trying to dereference it, unless you are absolutely sure it points to valid memory.
Rule 2. Initialize pointers and never dereference a null one. Check first.
Exactly. The source also briefly mentions pointer arithmetic. This is a bit unique. When you add an integer to a pointer, like PTR plus 1, the pointer doesn't just move forward by 1 byte in memory.
What does it do?
It moves forward by one size of data to pepper pointsto bytes. So if PTR is an int and its size of int is 4 bytes on your system, PTR plus 1 calculates the address of the next integer in memory 4 bytes away. PTR plus 2 would be 8 bytes away, and so on.
Ah, it scales by the size of the type it points to. That sounds useful for arrays.
Incredibly useful. Which brings us to the very close relationship between pointers and arrays in C++ on.
How are they linked?
They are intrinsically linked. In many, though not all, contexts in C++N, the name of a C-style array automatically decays into a pointer to its very first element. So if you have int numbers 10, just using numbers in an expression often behaves like a pointer to number 0.
So you can use pointer arithmetic to access array elements.
Yes. Numbers plus 0 is equivalent to number 0. Numbers plus 1 is equivalent to numbers 1, and so on. This pointer decay is why when you pass a C-style array to a function, the function actually receives a pointer to the first element, losing the size information.
We'll come back to that array issue. What about void pointers? Void. They sound generic.
A void is a generic pointer type. It can store the memory address of any data type, an int, a float, an object, anything. However, because the compiler doesn't know what type of data it actually points to, you cannot dereference a void directly using the operator.
So how do you use the data it points to?
You must first explicitly cast the void to a pointer of the correct specific type, like int or myClass, before you can dereference it and access the data. Void offers flexibility but sacrifices type safety, so it's used in specific situations like some C library interfaces or low-level memory manipulation, but generally avoided in modern C++ where possible.
Okay, less type safe, use with caution. The source really hammers home the dangers of pointers, beyond just null pointers.
Yes, it warns about two other major problems: wild pointers and dangling pointers. A wild pointer is simply an uninitialized pointer. It holds some random garbage address. If you try to dereference it, you're reading or writing to an unknown, potentially critical part of memory. Very dangerous.
Initialize your pointers. Got it. What are dangling pointers?
Dangling pointers are perhaps even more insidious. A dangling pointer is a pointer that used to point to valid memory, but that memory has since been deallocated or freed, for example, using delete, which we'll cover. The pointer variable itself might still hold the old address, but that address is no longer valid.
So it points to memory that's been given back to the system.
Exactly, or memory that might now be used for something completely different. If you then try to use that dangling pointer to read or write data, you are again causing undefined behavior. This could corrupt other data in your program in subtle ways, lead to crashes much later, or seem to work sometimes and fail others. Extremely hard to debug.
Undefined behavior again. These pointers seem like they require extreme care.
They do. This duality is the core of the pointer challenge. The power for efficiency, direct memory manipulation, and building complex data structures is immense, but it places a significant burden of responsibility on you, the programmer, to manage these addresses, meticulously ensuring pointers are always initialized, never null when dereferenced, and never dangling.
It's a lot to keep track of manually. The guide also notes that a pointer size itself is usually consistent on a system.
Yes, for example, on a 64-bit operating system, a pointer variable, whether it's an int, double, or myClass, typically takes up 8 bytes of memory itself because it just needs to store a 64-bit memory address. The size of the pointer is independent of the size of the data it points to.
Okay, that makes sense. It just stores the address. All right, let's talk about organizing collections of data. Arrays are common. The source compares the traditional C-style arrays versus std.vector versus std.array.
These are different ways to store a sequence of elements where all elements have the same data type. C-style arrays, inherited directly from C, are the oldest form. You declare them like int numbers 10 to create an array named numbers that can hold 10 integers.
What are their key characteristics, the pros and cons?
Well, they store elements contiguously in memory, which is good for performance. Accessing elements is done using a zero-based index in square brackets, like numbers 0, numbers 1, etc., up to numbers 9 in this case. Very direct access.
Okay, simple declaration, direct access. What are the downsides? The source seemed critical.
They have several significant limitations that cause major problems in practice. First, their size is fixed at compile time if declared locally on the stack like this, or when allocated dynamically. You can't easily resize a C-style array once it's created.
Not flexible.
No. Second, and critically, they have no inherent size tracking. You might think you can get the size, and the size of work trick does work, but only within the same scope, the same function, where the array was originally defined with its size.
Only where it's defined. What happens if you pass it to another function?
This is the killer. When you pass a C-style array to a function, it decays into a pointer to its first element. The function receiving it gets an int, not an array with size information. It has absolutely no idea how large the original array was unless you pass the size as a separate argument. Forgetting to pass the size or passing the wrong size is an extremely common source of errors.
The array decay problem leads to accessing memory you shouldn't.
Exactly. Which brings us to the most dangerous limitation: no bounds checking. If you have int numbers 10, the valid indices are 0 through 9. If you try to access numbers 10 or numbers 1, C++ does not stop you. There's no automatic check.
It just lets you read or write outside the array's memory.
Yes. This is undefined behavior. Your program won't necessarily crash immediately. You might read garbage data, or worse, you might overwrite some other important variable or internal program data located next to the array in memory, leading to bizarre, hard-to-find bugs or security vulnerabilities.
Buffer overflows. That sounds like a nightmare. Fixed size, loses size info when passed, no safety net for out-of-bounds access.
It really is a recipe for disaster in large programs. This is precisely why modern C++ offers much better alternatives from the standard library, specifically st.vector.
st.vector, the dynamic array we keep hearing about. How is it better?
std.vector, defined in the vector header, solves most of these problems. Its primary advantage is dynamic size. It can grow or shrink its capacity at runtime as you add or remove elements.
How does it manage that?
It manages its own memory automatically on the heap, that dynamic memory area we'll talk more about. When you add elements and it runs out of space, it automatically allocates a larger chunk of memory, copies the existing elements over, and then adds the new one. You don't have to do the low-level new-delete memory management yourself.
Automatic memory management is a huge plus after talking about the dangers of manual pointers.
Absolutely. And std.vector offers rich functionality through member functions. Pushback value adds an element to the end easily. Size tells you how many elements are currently in it, tracks its own size. Empty checks if it's empty.
And for accessing elements, does it have bounds checking?
Yes, it offers both. You can use the .index member function, like myvector.ati. This provides bounds checking. If the index I is out of range, less than 0, or greater than or equal to size, we'll throw a std.out-of-range exception, which is a safe way to handle the error.
Throws an exception instead of causing undefined behavior.
Much safer.
Much safer.
You can also still use the square bracket operator, like myvectory. This behaves like C-style array access. It's potentially slightly faster because it does not perform bounds checking. So the rule is use that when you need safety or aren't 100% sure about the index. Use only when you are certain the index is valid and need maximum performance in that specific spot.
Good distinction. Add for safety, for speed if you're sure.
Right. Plus, std.vector is fully STL compatible. It works seamlessly with all the standard algorithms like std.sort, std.find, etc. And thanks to modern C++ features like move semantics, C++11, they can be returned from functions efficiently without expensive copying. It's really the go-to dynamic array container in modern C++.
Okay, vector sounds like the clear winner over C-style arrays for dynamic needs. What about std.array? You mentioned that too.
std.array, introduced in C++11 and found in the array header, is kind of a middle ground. It's a fixed size array, just like C-style arrays. The size must be known at compile time and is actually part of the type itself. You declare it like std.array 10 scores.
So size is fixed at compile time like a C-style array. What's the benefit then?
It wraps a raw array, but provides a much safer, more convenient STL-compatible interface. Crucially, it does not decay into a pointer when passed to functions. A function receiving a std.array 10 knows it's an array of 10 integers. It retains its size information, which you can access using the .size member function.
So it fixes the size loss problem of C-style arrays.
Yes, and it also offers both .index with bounds checking and operator without bounds checking, just like std.vector. Because its size is fixed at compile time, std.array is often allocated directly on the stack if it's a local variable, making it very lightweight and efficient for small, fixed-size collections where you still want the safety features and the ability to use STL algorithms easily.
So if you need dynamic size, use std.vector. If you know the size at compile time, and it won't change, std.array gives you efficiency plus safety and STL compatibility.
That's a perfect summary. The source strongly recommends preferring either std.vector or std.array over raw C-style arrays in almost all new C++ code. This evolution reflects a major shift towards safer, more robust container management in the language. The guide's comparison table is great for quickly seeing the key differences in size, memory, size tracking, and bounds checking.
Make sense? Let's move on to handling text, another area with old versus new, C-style strings versus std.string.
Right, handling sequences of characters text is incredibly common. C++ inherited C-style strings directly from C. These are not a built-in type per se, but rather a convention. They are simply arrays of char that are terminated by a special null character, which is represented as a 0.
The null terminator 0. Why is that important?
It's the signal that marks the end of the string. Functions that work with C-style strings, often found in the string header, rely on scanning through the character array until they hit this 0 to know where the string data actually stops.
So literal strings in double quotes like hello, are they C-style strings?
Under the hood, yes. When the compiler sees hello, it creates a character array containing H, E, L, O, and automatically appends the 0 at the end, so it actually takes up 6 bytes of memory.
Okay, and manipulating them uses functions from string.
Yes. Functions like stripey to copy strings, streetin to concatenate append strings, stralin to calculate the length, which counts characters up to but not including the 0, and strimpy to compare strings lexicographically.
What are the main disadvantages of using these C-style strings and functions? The source seemed even more critical here than with arrays.
The biggest issue, by far, is the risk of buffer overflows combined with manual memory management if the strings are dynamically allocated. Functions like stropy and stracat are notoriously dangerous. They take a destination buffer, a char array, and a source string, but they have no idea how big the destination buffer actually is.
They just start copying?
They just start copying characters from the source to the destination until they hit the 0 in the source. If the source string, plus its 0, is longer than the destination buffer can hold, Stropy will just keep writing bytes past the end of your allocated buffer, overwriting whatever happens to be next in memory.
That sounds identical to the array out-of-bounds problem, but maybe even easier to trigger accidentally with text.
Exactly. This is a major source of bugs, crashes, and historically countless critical security vulnerabilities in software. Beyond buffer overflows, there's no inherent size tracking. Functions constantly have to rescan for 0, which can be inefficient, and you always need to remember to allocate n+1 characters for a string containing n actual characters just to fit that null terminator. It's cumbersome and error-prone.
Manual, inefficient, risky. Seems like we need a better way.
And we have one. The standard library provides std.string defined in the string header, note .string, not string.h, or cstring. This is part of the STL and is the modern, safe, convenient, and powerful way to handle strings in C++.
How does std string solve the problems of C-style strings?
Primarily through automatic memory management. A std.string object manages its own internal character buffer, typically allocated on the heap. It automatically handles allocation, reallocation if the string needs to grow, and deallocation when the std.string object is destroyed. Thanks, RAII. You don't have to worry about new char or delete or calculating buffer sizes.
So no more manual memory juggling and much lower risk of buffer overflows.
It drastically increases safety and convenience. Because std.string knows its own size and capacity, operations like appending or assigning are managed internally to prevent simple overflows that plague struct. It also offers rich functionality directly through member functions and overloaded operators.
Like using plus for concatenation.
Yes. You can just use the plus operator to concatenate std.string objects. You can use comparison operators like seeoid directly to compare strings lexicographically. There are member functions like .size or .length to get the length. They return the same value. .index or operator for character access, again, has bounds checking doesn't. Find to search for substrings, .insert, .replace, modify the string, and even push back to move single characters at the end.
It sounds much more intuitive and packed with features like std.vector.
It is. It behaves much more like string types in other modern languages. And if you ever do need to interact with an older C library function that expects a null-terminated C-style string, std.string provides the .cstr member function, which returns a temporary const-char pointer to its internal null-terminated data.
So you have an escape hatch for compatibility when needed.
Exactly. But the source's recommendation is crystal clear.
Use std.string.
Absolutely. It strongly advises using std.string for virtually all string handling in new, modern C++ code. While understanding C-style strings is necessary for dealing with legacy code or C APIs, std.string is vastly safer, more convenient, more powerful, and less error-prone for your own development. The comparison table in the guide really highlights the stark differences in memory management, safety, and ease of use.
Okay, another win for the modern standard library. Now let's dive deeper into a topic that's intrinsically linked to pointers and containers like vector and string that manage their own memory. Memory management itself. specifically stack versus heap and the manual operators new and delete. The source emphasizes this is crucial for efficiency in writing bug-free code.
It truly is fundamental to understanding how C++ programs work under the hood and why things like smart pointers are so important. Programs generally use memory from two main regions, the stack and the heap, which C++ often calls the free store.
Let's start with the stack again. How does that work in more detail?
The stack is a region of memory managed automatically and very efficiently by the compiler and the operating system. It's primarily used for storing things with a well-defined lifetime tied to function calls. Local variables declared inside functions, function parameters passed by value, and internal call stack information, like return addresses so the program knows where to go back to when a function finishes.
And it's known for being very fast for allocation and deallocation.
Extremely fast. When a function is called, a block of memory, a stack frame, is reserved on top of the stack for its local variables and parameters. This is typically just adjusting a single pointer, the stack pointer. When the function returns, that stack frame is simply popped off again, usually just adjusting the stack pointer back. It follows a strict last in, first out LIFO order, like a stack of plates.
Simple and efficient. What's the catch?
The main limitation is that the stack has a limited fixed size, typically determined by the operating system or compiler settings, maybe a few megabytes. If you try to allocate too much memory on the stack, for instance, by declaring a very large local array inside a function, or through excessively deep recursive function calls, you can exceed this limit, resulting in a stack overflow error, which usually crashes your program.
Okay, so automatic, fast, LIFO, but size limited. What about the heap or free store?
The heap is a much larger pool of memory available to your program, and it's used for dynamic memory allocation. This is where you allocate memory when the size isn't known until runtime, or when you need the allocated memory to exist beyond the lifetime of the function that created it.
Is the heap also managed automatically like the stack?
No, and this is the absolute critical difference and the source of many traditional C++ headaches. Memory on the heap is manually managed by the programmer using the specific C++ operators, new to allocate memory and delete to deallocate free it.
Manual management.
Yeah.
That sounds like where the trouble starts. Is it slower than the stack too?
Generally, yes. Allocating memory on the heap new involves more overhead. The memory management system has to find a suitable contiguous block of free memory of the requested size, which can take time and might involve more complex bookkeeping. Deallocating delete also involves overhead to mark the memory as free again, potentially merging it with adjacent free blocks. More importantly, memory allocated on the heap has a lifetime completely independent of the scope, the function call, where it was allocated using new.
So it sticks around.
It persists until it is explicitly deallocated by the programmer calling delete on the pointer that holds its address. If you don't call delete, that memory remains allocated for the entire duration of your program.
So manual management using new and delete is where the difficulty and common errors creep in.
Absolutely. Manual memory management is notoriously difficult to get right consistently, especially in complex programs with multiple interacting parts, long-running processes, or when dealing with error conditions like exceptions. The two main, very serious pitfalls are memory leaks and dangling pointers.
We mentioned dangling pointers before. Remind me about memory leaks in this context.
A memory leak happens if you allocate a chunk of memory on the heap using new, get a pointer to it, but then you somehow lose that pointer without ever having called delete to free the memory.
How could you lose the pointer?
Maybe the pointer variable goes out of scope, or you overwrite the pointer variable with a new address from another new or null PTR before deleting the old memory. Once you lose the only pointer to that heap allocated memory block, your program can no longer access it or deallocate it.
But the system still thinks your program is using it.
Exactly. The memory is effectively lost, unusable by your program, but not returned to the system's pool of available memory. If your program runs for a long time and keeps leaking memory like this, it can gradually consume more and more system resources, eventually slowing down the entire computer or causing your program or others to crash when they can't allocate needed memory. Tracking down leaks can be very difficult.
That sounds like a slow creeping kind of problem. Nasty.
It can be. And then there are dangling pointers again, specifically related to delete. A dangling pointer is created when you do call delete on a pointer to free the heap memory it points to, but you, or some other part of your code, still hold on to a copy of that pointer variable, which now points to deallocated memory.
So the memory is free, but the pointer still has the old address.
Right. If you then try to use that dangling pointer either to read from the memory in text dangling PDR, or even worse, write to it, dangling PDR ace 10, you are invoking the dreaded undefined behavior. You're interacting with memory that the system now considers free or might have already reallocated for completely different data. This can cause immediate crashes, like a double free error if you accidentally call delete on it again, or much worse, silent memory corruption, where you overwrite unrelated data, leading to bizarre bugs that are incredibly hard to trace back to the original dangling pointer access.
Okay, so new allocates on the heat and gives you a pointer. Delete frees the memory that pointer points to.
Yeah,
But you have to be extremely careful to call delete exactly once for every new and not use the pointer after delete.
precisely. The new operator allocates memory for a single object, new int, or an array of objects, new int 10 on the heap, and returns a pointer to the start of the allocated memory. You can also initialize the memory during allocation, like new int 100 or new my class, arg1, arg2. If new fails to allocate the requested memory, for example, the system is out of memory, by default it throws a std.bottlelock exception, which will terminate your program if not caught. There's a nothrow version, new std.nothrow type, that returns null PTR on failure instead.
And delete is the counterpart.
Yes. The delete operator deallocates memory previously allocated with new, but the source emphasizes a crucial rule you absolutely must follow. You must match the allocation form with the deallocation form.
Match them.
If you allocated a single object using new type, you must deallocate it using delete pointer. If you allocated an array of objects using new type size, you must deallocate it using delete pointer. Note the square brackets after delete.
Delete for single objects, delete for arrays. What happens if you mix them up?
Undefined behavior. Using delete on memory allocated with new, or using delete on memory allocated with new for a single object is a serious error. The compiler might not warn you, but at runtime it can lead to heap corruption, crashes, or incorrect destructor calls for objects in an array. You have to get the pairing right.
Wow. That requires meticulous attention to detail and perfect bookkeeping throughout your code.
It absolutely does. This strict requirement for manual matching, combined with the risks of leaks if delete is forgotten, especially if an error or exception occurs between new and delete, and the dangers of dangling pointers if you use a pointer after delete is the primary reason why manual memory management with raw and new delete is considered so error-prone and difficult in C++ lead.
Which leads us back to modern C++ having better solutions.
Exactly. The source correctly points out that because of these significant dangers and the difficulty of getting manual management right 100% of the time, RAII, resource acquisition as initialization, and smart pointers like std.unicaptr and std.sharedbtr are strongly emphasized and preferred in modern C++ code. They automate the cleanup process, drastically reducing the need for direct calls to new and especially delete. We'll dive into those smart pointers soon. They are a game changer for C++ safety.